Okay, so in this video, we want to find the following limit using L'Hopital's rule. But before we try to apply L'Hopital's rule, let's figure out what kind of case we're dealing with. Well, as x goes to infinity, ln of x also goes to infinity. And as x goes to infinity, x squared also goes to infinity. So the case we're dealing with is an infinity minus infinity case. Let's see before we try to manipulate this, because as clearly we cannot use L'Hopital's rule yet, as we don't have a 0 over 0 case or an infinity over infinity case. But let's see with our intuition of how large ln of x really is and how large x squared really is, at least relative to each other. Let's see if we can guess what the answer should be. And then we will proceed to prove that we are right using L'Hopital's rule after a simple algebraic manipulation of the expression. So, if we produce a rough sketch of both ln of x and x squared in the xy plane, so here's y equals ln of x, and here's y equals x squared. We can clearly see that as x goes to infinity, x squared will increase to infinity much faster than ln of x. So sure, ln of x is big when x gets large, but x squared is so much bigger that this term should really take over, and so we expect, because x squared is so much bigger than ln of x is, for large values of x, we expect this term to take over, and that the limit therefore will end up being negative infinity. To prove that we are right, the idea is first to factor the dominant term, the larger term being the x squared, out of the expression. So if we factor x squared out of the expression, then the ln of x to compensate must become ln of x over x squared, minus, of course, 1. If you want to check multiply through by x squared, these cancel, you retrieve ln of x squared times negative 1, negative x squared. What's interesting now, if we focus on this quotient, then as x tends to infinity, ln of x tends to infinity, x squared tends to infinity, so this alone gives us an infinity over infinity case. So let's take this limit aside, and we'll be able to apply L'Hopital's rule. As we've just said, we have an infinity over infinity case, and we now apply L'Hopital's rule. The limit as always stays the same. X tends to infinity. Replacing ln by its derivative, the derivative of ln of x is simply 1 over x, over the derivative of x squared, which is 2x. If we simplify, we have quite simply 1 over 2x squared. And now the limit is trivial. As x goes to infinity, 2x squared goes to infinity, and so 1 over infinity shrinks to 0. And so you see, as x tends to infinity, ln of x over x squared, by L'Hopital's rule, does shrink to 0. And so, let's look at the case that we're dealing with now. Well, obviously, as x goes to infinity, x squared goes to infinity, times, and this is where it's interesting, we have proved with L'Hopital's rule that this limit is equal to 0. So ln of x over x squared goes to 0 as x tends to infinity. So this term, since the first approach is 0, will be approaching 0 minus 1, which is negative 1. But now the limit is trivial. We have a product of two functions, and as x tends to infinity, the first function gets bigger and bigger and bigger and positive. The second function is approaching negative 1. So in the end, the limit is negative infinity. And you can see that our intuition was right. If you think about what this is saying, which also corroborates the graph of the two functions, as x tends to infinity, ln of x over x squared approaches 0, which means that even though ln of x is big, when x tends to infinity, ln of x is infinitely small compared to x squared. So if we go back, the intuition is that the ln of x doesn't really matter, and only the negative x squared matters, which gives us a limit that is negative infinity. And that's it.